Okay, welcome back then, everybody, and we will continue with the fourth part of my lectures where we're looking at reaction mechanisms. Okay, so just to recap where we got to before. So what we've been looking at previously was nucleophilic substitution reactions, where we'd been looking at a nucleophile being involved in a reaction with a substrate where a leaving group departs. So effectively we're doing a substitution because the nucleophile is replacing the leaving group. And we looked at SN1 and SN2, which had different mechanisms and different stereochemical outcomes. So last time we finished by saying that a competing reaction to the nucleophilic substitution reactions are elimination reactions. And in elimination reactions, what happens is a base is going to remove a proton from a molecule. A leaving group is also going to be present in the molecule, and that will break away. And the overall product is making an alkene. So what we're going to do today is look at the mechanisms for these elimination reactions, and we're going to look at the stereochemical outcome. We're going to follow a very similar pattern to the way we approach the nucleophilic substitution reactions. So we're going to be looking at two different classes of mechanisms that can occur for elimination reactions, and we'll see what the stereochemical outcomes will be. So the first one we're going to look at is the E1 mechanism. So E for elimination, 1 for unimolecular. So in the E1 mechanism, I've written out here the generic reaction mechanism. So remember, that's one that can apply to any E1 reaction. We're not stipulating the exact details of the substrate or what the base is or what the leaving group is. It's generic. And as we've said for the SN1 and the SN2 generic reaction mechanisms, you should learn this one. You should learn the generic reaction mechanisms so that you can demonstrate an understanding of the key steps. So in this E1 mechanism, we've said it's unimolecular, so there's only one species is going to be involved in the rate determining step, and that's our substrate. So in the rate determining step, the first step is going to be the loss of the leaving group. So remember, the leaving group is pulling electrons towards it, so our electrons are flowing towards the leaving group using this curly arrow. And when we lose that leaving group in that rate determining step, we end up with a carbocation. So in the second step, because it's an elimination reaction, our base is going to pull off a hydrogen, push the electrons round to make the alkene. So this is our alkene which is being formed. These are carbons at the end. They're going to have substituents on them, but because it's generic, we're not going to stipulate what they are. And our base is going to have pulled off the hydrogen, so it's now got the hydrogen attached to it. Our leaving group in this first step departed, taking the electrons with it, so it's Lg-. So this is the E1 mechanism. It says up here what's going to happen is our hydrogen to carbon bond and our carbon to Y is the leaving group. They're going to be broken separately in two steps. So that's what we've seen. This breaks off first in the first step, and then the hydrogen to the carbon bond breaks by attack of the base in the second step. Because we're breaking this off first, we're going to form a carbocation. And so, yeah, it's very reminiscent of the SN1 reaction, remember, where we lose our leaving group in the first step to give a carbocation. So, yeah, when we're looking at revising for this, if you can remember the features of the SN1 reaction, so loss of the leaving group to give a carbocation, that's the same first step for the E1 mechanism, loss of the leaving group to give a carbocation. And it's because those first steps are identical that they are competing reactions. So hopefully it's clear from what I've said what the essential features are for the E1 mechanism. I've also produced another one of these sort of live videos where I actually write all of this out from scratch. So go through that as well, just to make sure that what I've done on that, writing it out from scratch, you would also be able to do, because it's important you understand the features of this generic E1 mechanism. So I'd also like you to have a look at this exercise just to give you a chance to recap on what we've already learnt for the SN1 reaction. So I'd like you at this stage to just look back at the SN1 reaction and remind yourself of the mechanism, remind yourself of the rate equation for the SN1 reaction, and hopefully when you do that you'll see that there are similarities between the rate equation for the E1 and the SN1 reaction. You'll be able to see that in terms of the rate determining step is only dependent on the concentration of this starting material substrate. It's not dependent at all on the concentration of the base, because that isn't involved until the second step, which is after the rate determining step. So have a go at that. You'll find the answers in your notes in terms of the mechanism for the SN1 reaction. So that's a generic reaction mechanism and the rate equation. Okay, so if we think about the stereochemical outcome, remember we've always thinking about isomers, because different isomers can have different biological and therapeutic properties. So in some cases we want to have a specific isomer because that's the one that has the high activity, maybe the other one has no activity, or maybe it's toxic. In other cases, maybe we don't mind if we get a mixture of isomers because maybe we don't know which one we want, so it gives us a chance to test both of them, or maybe both have the same beneficial activity. So again, that wouldn't matter, but we need to know what's the case, and we need to have reactions which will give access to the appropriate single isomer or mixture of isomers. So when we think about the E1 reaction, we're making a carbocation. And carbocations have a finite lifetime, so they're actually detectable. And because they have a finite lifetime, it gives them a chance to equilibrate. If there's a more stable form, it can go from a less stable form through to the more stable form, and that can lead to the ratio of the products being altered. So what we're going to see is that when we look at the E1 reaction, the carbocation has a finite lifetime. So that means that we can get rotation around the single bonds to give mixtures of different isomers of that carbocation. And because that can occur, we can get mixtures of different isomers of the product. So even if we had one isomer of starting material, in the E1 reaction, we will get mixtures of E and the Z isomer. And we're going to see this specifically for an example on the next slide. So I'm going to run through this because this will exemplify why we get a mixture of the E and the Z isomers from E1 reactions. But again, I've got a walkthrough video for this, which I've uploaded to Blackboard, where you'll be able to see me going through this again, sort of writing things in real time. Okay, but let's have a look at it. So here we've got our starting material, and this is the molecule, the substrate, which is going to undergo the E1 reaction. So we're told it's E1. You wouldn't need to necessarily work out from this if it was E1 or E2. We're telling you it's an E1 reaction. So if it's E1, we know in that first step, in the generic rate equation, we're going to lose our leaving group to give a carbocation. So if we look at our molecule, our substrate, we have to work out where's a group which can be a leaving group that when it departs is going to give a carbocation. So we've got this hydroxy group here. We've seen this as a leaving group in our nucleophilic substitution reactions. When it reacts with acid, it converts it into a better leaving group than the hydroxide itself. So this will then break off, the electrons will push onto that as the leaving group. This carbon here has then lost electrons, so it's positively charged. So that's the first step of our E1 reaction, will be loss of the leaving group to give a carbocation. So in this carbocation, this is where we're talking about we can get rotation around carbon-carbon bonds, which will give us different isomers of product in the E1 reaction. So if you think about the groups here, we've got a phenyl group and we've got a methyl group, which are appended to this carbon-carbon bond. So if we were to rotate around this carbon-carbon bond here, we can see an example where the phenyl and the methyl could be opposite, or by rotating around here, we could have an example where the phenyl and methyl are on the same side. This again would rotate around this carbon-carbon bond to take it back to this form. So because this carbocation, which is formed from the loss of the leaving group, has a finite lifetime, we're going to get equilibrium between these two to give us two extremes where we have the phenyl and the methyl on opposite sides, or the phenyl and the methyl on the same side. So then when we do our removal of the hydrogen in the second step of this E1 reaction, and again, this is what you'll see on the walkthrough video, when we lose the hydrogen, it could feed in here to make the double bond in that second step. and the product from this would have the phenyl and the methyl on opposite sides. Or if we lost a hydrogen from this form here, so if the hydrogen was lost, electrons push in, that would then give the alkene with the phenyl and the methyl on the same side. So what we see in the E1 reaction, as I've exemplified here, is when we do the reaction, we will get a mixture from the E1 reaction, excuse me, of the E and the Z alkenes. The reason being that the carbocation that we form has got a finite lifetime, so we're able to rotate around this carbon-carbon bond to influence where these groups are, whether they're on opposite sides, giving us this alkene, or the same side, giving us this alkene. So have a look at this walkthrough video where I go through this in real time, showing you how we lose the leaving group, how we lose the hydrogen to get through to the different products. But the take-home message from this is that the E1 reaction is going to give us of the alkenes, but we're not going to get a 50-50 mixture of them. We're going to find that the one which is more stable is the one which is going to be formed in excess. And if you think about which is more stable, we can think about stability of the carbocation, because the stability of the carbocation will influence the stability and the ratio of the products. So hopefully you can imagine here where we've got a bulky group for the phenyl and a bulky group for the methyl. If they're on opposite sides of this single bond, that's going to be much more stable than if they're on the same side of the single bond. If they're on the same side, you've got a bulky group here with electron density. It's going to clash with the group here, also with electron density. That's not going to be as favoured as if the bulky group here is pointing away from the bulky group up here. So if this one is more stable, it is going to equilibrate. We are going to get some of this, but this will be the predominant form. That means when we lose our hydrogen in the elimination reaction, this will be the predominant form because there's more of this in this mixture. So this will form in excess compared to this one. So that's what we've got here, that generally when we've got E1 reactions, we will get a mixture, but we will predominantly get the E alkene. So remember from Dr. Sarah Allman's course, we've got nomenclature to show E versus Z. So make sure you're happy with that by way of revision. The reason we predominantly get the E alkene is because this here is lower in energy. Now notice here I've said transition state. It's not a transition state, it should be an intermediate. So make sure you change that. It should be an intermediate, leading to it has lower energy. We do get some of the Z alkene because we've also got some of this, but it'll be lower quantity compared to the E. Okay, so that's what you need to know for the E1 reaction. We lose our leaving group in the first step to give a carbocation intermediate. When we lose our hydrogen in the second step, we're going to always get a mixture of the alkene products, but generally we'll get more of the E alkene than the Z because the intermediate, which leads to that, is lower in energy. So again, to exemplify this point, I've got an example here, which again, you'd never have to draw out. You don't need to remember the structures of this, but if the scheme was given to you, you should be able to rationalise what is happening. And it's an example of where we make tamoxifen, which is an important drug for the treatment of breast cancer. So here we've got the tamoxifen products, and we've got it as a mixture of the E and the Z forms. So it occurs, the reaction occurs to make a mixture, as we've seen on the previous slide. So how does this reaction occur? This is the substrate, and in the rate determining step, because it's E1, we're going to lose our leaving group to give a carbocation intermediate. So we'd look at our molecule and we'd think, where is a part which can be a leaving group under acidic conditions? So again, we've got a hydroxy group here, which will react with the acid to make a very good leaving group, and the electrons will then push out that leaving group, breaking the bond to give a carbocation. This is very stable carbocation. If you remember when we looked at SN1 reactions and we looked at factors which affect the stability of carbocations, we saw that if you have resonance where you can spread positive charge around double bond structures, that could make it stable. So here we've got a double bond, single bond with the plus, so these electrons could feed in to make that stable. Double bond, single bond with a plus, so again we've got resonance here. So this is going to be a very stable carbocation, which means loss of that leaving group in the first rate determining step will be favoured. So it's E1 because we get loss of the leaving group in the rate determining step. In the second step, our base would pull off the hydrogen, push the electrons in to make the alkene. So it's a perfect example of the E1 reaction in practice because we're losing our leaving group in the first rate determining step. We're making a stable carbocation, and then loss of the hydrogen from that gives us a mixture of our E and our Z alkenes, and that's the structure of tamoxifen, which can be used in the treatment of breast cancer. Okay, so we're nearly there with the new mechanisms that you need to learn from this course, because the last one we're going to look at is the E2 mechanism. So we're still looking at elimination, so it's still E because it's elimination, but now it's 2 because it's going to be a bimolecular process. So we're going to have 2 species involved in the rate determining step. And again, this is going to be very similar to what we saw for the SN2 reaction, where we had 2 species involved in the rate determining step. So in our E2 mechanism, rather than just lose the leaving group in the first step, as we do for the E1 reaction, what we're going to do is we're going to have our base pulling off our hydrogen, pushing electrons round, all at the same time as the leaving group departs. So because we're partially forming a bond here, partially forming the double bond at the same time as we partially break that leaving group, we're going to have a transition state. So we're going to draw our transition state in the square brackets with this sign here to show it's a transition state. And what we're getting, remember, we can use these dotted lines for partial bond formation or breakage. So we've got a partial bond forming between the base and the hydrogen, partial bond breakage between the hydrogen and the carbon. We've still got this bond here because that was present in the first place, but we've now got another partial bond forming. So it's starting to form the alkene double bond, and we've got partial breakage to the leaving group. So that's our transition state. We've got our base and our substrate involved at the same time. And when the transition state, we've formed the bonds completely and we've broken the bonds completely from the transition state, we get our product, which is the alkene. Our base has now got the hydrogen attached and our leaving group has departed. So this again is a generic mechanism. We're not stipulating what else is on the carbon. We're not stipulating what the base is or what the leaving group would be. It's a general mechanism that could be applied to any E2 mechanism. And it's another one that you must make sure you can learn and you can understand. So hopefully you're having a look at these additional walkthrough videos which I provided, and you'll find another one for this generic E2 mechanism. So have a look at that, where I'll walk through this in sort of real time, showing you exactly what's happening. So that's the elimination bimolecular reaction. So another little revision exercise for you to do. Just remind yourself of the mechanism and the rate equation for the SN2 reaction. You'll see that there's great similarities between the E2 and the SN2. So again, when it comes to revision, if you learn one, that should really help you to understand what you need to add to for the complementary reaction. So if you learnt the SN2, you would only have a little bit extra to learn for the E2 because of the similarities. So again, in E2 eliminations, it's bimolecular. So when we think about the rate determining step, both the base and the substrate are involved in that rate determining step. So that will be reflected in our rate equation. So rate will equal a constant times the concentration of the base times the concentration of the substrate. So if we have a strong base, or if you have a high concentration of base, that will affect the reaction. It will increase the rate of reaction. That's similar to the SN2 reaction, where we saw that the rate of the nucleophile, sorry, the concentration of the nucleophile was important for the rate. So that's, yeah, shown you some of the similarities. So again, I've got some specific examples of molecules that have been made using the E2 reaction. So this here is a molecule which was helpful as an antiviral agent. It's got similarities to sort of the base pairs which are found in DNA, and it's effective as an antiviral agent. So if it's an E2, again, you would never have to work out, is it going to be E1 or E2, what type of reaction you would be told. So here we've been told that it's an E2 mechanism. So it's going to be an elimination and it's going to be bimolecular. So if it's elimination, we're making an alkene, And if it's bimolecular, we're having both the base and the starter material substrate involved in the rate determining step. So this step here is our E2 reaction. We can see we're making an alkene. This is the alkene which we're introducing. So we're going to make that alkene via the removal of a hydrogen and the removal of a leaving group. So if we were to look at our molecule here, if we're making the alkene here, we're going to be doing some reaction sort of across this area here, aren't we? Because this is where we're going to be making the extra bond to give us the double bond. So we've got a hydrogen here, which is nicely shown. We're told we've got a strong base. So we can imagine a base can come in and pull off that hydrogen, kick the electrons round to kick out a leaving group. Now this here you haven't seen before. It's tosylate para-toluene methyl sulfonate group. You wouldn't need to know the details of it, but I've shown you the structure here. So the idea here is that this is going to be kicked out as a leaving group. So our base will come in, pull off the hydrogen, feed electrons round, kick that out as a leaving group. So I've shown you when that happens, we make our double bond by the transition state and we get this as our leaving group. Now we've spoken a couple of times now about resonance, and so this is a particular leaving group which is useful because it's very stable due to resonance. So this part here is the part we're going to be looking at, which is going to be involved in resonance because we've got a single bond with a charge connected to a double bond. So resonance, remember, is where you can stabilise the charge through the pi framework. So we've got the opportunity to stabilise the charge through this double bond or through this double bond. So this is a very good leaving group due to resonance. So if it's a very good leaving group, it means that we can do the E2 reaction when the base comes in, pulls off the hydrogen, kick the electrons round, lose this as a leaving group all in one step. So we've got another mechanism, another exercise here. And what I'd like you to do is to just check you are happy with this term resonance, which we've spoken about a few times. And I want you to then draw some resonance forms for that anion on the previous slide. So for this anion here, I want you to try and think how the electrons could be distributed so they're not just on this oxygen here, single bond, but how they could spread out between the double bonds here. Okay, and again, I've given you a walkthrough video with the answer for this, so have a go at it, remind yourself what resonance is, and then think what the tosylate anion could do in terms of that resonance. Try and draw out some arrows, but have a look at this video. If you get stuck even getting started, have a look at the video because there's certain places where you could pause it so that you can demonstrate how exactly it can spread out, not just through one double bond, but also through the other double bond. So by going through this exercise, hopefully you'll learn and really sort of consolidate your knowledge about resonance. Okay, so what we're going to do in the next part of the lecture is think about the stereochemistry of the E2 reactions in the same way that we've done for E1, for SN2 and for SN1. So I'm going to pause there, and when we start next time, we're going to be looking at the stereochemical consequences of the E2 reaction, and again we'll talk about that in terms of what it means for particular isomers that could be made by the E2 reaction. Okay, so hopefully that has given you a chance to practice certain features of mechanisms. Any questions, as always, just drop me an email and I'll do my best to help you. Thank you.